please stop over there. They'll be up for a while and read. It looks like they worked really hard on those, and they are on a variety of different topics. So I wanted to also say thank you to our SPEAR team this year for all of your hard work, not only with the research that you guys have been doing, but with all of the help that you guys provide to do with all of our K-12 outreach, our community outreach. We have lots of planetarium shows we've been given all over the place. And so thank you. It is a lot of work, and it takes a team to make all of this stuff happen. With that said, we have our first students coming up with Project Mango. If you did not get a program, just let us know, put your hand up, and we can give it to you if you'd be interested in getting it. And then if you would, before you leave, if you would sign in for us, it does help us kind of track how many people attend these types of events. So Zach and Kayla.
Howdy. Pretty much everybody here knows me. So I'm Zach. If you don't, nothing is working. There it goes. If you know me, you've probably heard me ramble about my program. I got my own little project going. Last year, I got to go to NASA, and we did a gap analysis on advanced air mobility. And one of the biggest gaps with advanced air mobility that we found was electric aircraft. The experimental aircraft that NASA has, it can only fly for 100 miles. Electric aircraft don't have a long flight range, and that 100 miles is a little two-seater Maxwell with 800 pounds of battery in it. So that's for a plane that's take off, fly around the airfield a couple times and land. So the big concept was that we were going to take some of so they've taken electrical energy out of the power cells. They're running it to a permanent magnet motor, spinning the motor, so turning electrical energy into kinetic energy. The idea is to recapture some of that kinetic energy from the propellers and return it back to the power bank as electrical energy. So how we do that, as you can see in the slides, got this awesome little picture over here on the right from the original project at NASA, where we put a cowl around the propeller. The cowl will be embedded with induction coils based off of Faraday's law of induction, magnets in the propellers. As the magnets pass the coils, voltage is created or generated. So that's you don't have to read the whole page. That's it in a nutshell. This is the actual X-57. This is NASA's prototype electric aircraft. It's just a little guy, like I said, with a 100-mile flight range. There's the motor, permanent magnet motor, very similar to like the type of motor you would think Tesla has, except instead of having the magnet as the core, the stator is the core, and the magnets surround it. Kind of cool concept. So I've been trying to make a successful mini model for a while. This is let's see, 1.1 never saw the light of day. 1.2, I think this is technically 1.3 being printed right here. Maybe it's 1.2, I don't know. Kind of lost track at the beginning. I just kind of was running off of a dream, but actually getting the first one printed, there it is, actually printed and assembled without the propeller. No induction coils in it. Just a simple guy. The wiring diagram for it, and anybody that knows anything electrical will notice that this is a two-phase system. One of the original forethought was the more coils the better, and I didn't really think about the tail end of it. So when I designed the cowl, we what was it we did? I can't remember exactly how many coils we did, but it wasn't divisible by 3. So we ended up with a two-phase system instead of a three-phase system. This is the wiring diagram all the way to rectification. It's a rough one. I think here it is actually spinning, and you can see in this version or whatever, the magnets are facing you. That's not ideal. I knew it wasn't ideal when we did it, but it was the easiest way to put the magnets in, and I was hoping it would all work out anyways. When I actually put a coil in it and spun it, I did create voltage, very, very little bit of voltage, and not enough to talk about actually. So then this was the end of last year. This year, I picked up an Orion internship from OSGC. Thank you for that. That allowed me to keep working on this, and I took it back to the drawing board, literally. So this is the wiring diagram for the current model 1.4, and I think we're on 1.4.1. And you can tell we have 3-phase system here. We're down to only 12 coils. However, at a 3-phase system, much bigger coils, much bigger cowl. Doesn't look like it with the naked eye, but measurements, it's significantly bigger coils that are embedded in it. I didn't know SolidWorks. I spent like 46 hours in the lab during December when we didn't have school, just teaching myself SolidWorks and redesigning this thing ground up. I actually should have thrown in one of the big things. It's not a huge thing, it's just a convenience thing, is you notice how this is mounted on. That means you have to put the cowl on before the propeller, which means you're trying to put the propeller on, which was a nightmare. So in the new design, I changed the mounting so it can go on over the propeller. And then 1.4, the cowl actually did change the dimensions, but 1.4 propeller, we thought we were being really clever and really cool. You have it set so you put a big magnet in the face, and then you slip a little magnet in this little tiny window, and it would slide up and would actually lock down the magnets, allowing them to face the coils, and the 2 magnets together would actually increase the flux. So we thought we were being really clever until I printed the things, put the magnets in it, and started to spin them, and they came flying out. So it didn't work like we wanted to. However, that is to date my favorite design of propeller that we've had. Version 1.4.1 over there on the right side. I don't really have a top down into the hole. It's just a extruded cut that lets big enough for the magnet to sit in, and just slightly deeper so I could actually put a snap ring in. There's a little groove in there. So that's how the current model, we literally have magnets inside this hole with a little snap ring holding them. We have gotten it up to speed. They do not fly out. So that's great. This slide is literally to commiserate all the pain and suffering that we've gone through trying to get the printers to cooperate. It was ridiculous. I have wasted so much of this year just trying to get things to print right. It is funny. I know I had to put it in because I literally, when it says hours, days, weeks, it's not joking. Like, I seriously lost so much time just trying to get the printers to work right. You finally figured out the issue, finally got it working right, and boom. Here's the 1.4.1 fully assembled. It actually can't really tell, but there is a coil on top. Those 2 red things coming off the top are the wires. And we actually, me and Derek the other day, we actually spun this thing with a coil in it, and we're generating real numbers. There's all the data right there. At about 10.5 volts in, 2,800 RPM, we were getting 420 millivolts back. That's 1 coil times 12. You're heavy speculation because there's going to be a lot more resistance and stuff, and this will not hold true. But at the moment, we're projected just shy of 50% return, which is more than I was hoping for. Yeah, so Like I said, once we get all the coils in there, there will be a Lenz's law, will create magnetic resistance. I will have to increase the power to maintain the rotations, which right there will lower the efficiency and stuff. There's a few other factors that'll come into play, but I'm still really like, my goal was to get it over 20%, hopefully over 40%, but over 20%, and it's relevant. It could be applied in real life to a real size motor and help increase the flight range of electric aircraft. At 40%, I'm ecstatic. So seeing this and running them, I was very happy with the numbers. Current numbers were a little weird, but we'll see what it looks like when we get everything, all the rest of the coils in. Coils take about 2 to 3 hours to wind per coil. It's a very slow and annoying process that was way more painful than I thought it was going to be. Gosh, it's so slow. It's not fun. But that is my entire presentation. I'm going to keep working on this until the dang thing is running. And by the end of this year, this school year, which is only what, 2 weeks, my goal is to have every coil in the cow and have a functioning mini model all the way through rectification. I'm going to be in here for like a week straight doing nothing but wrapping coils and soldering wires, but yeah, so.
You do have help though.
I know, I do have help. I'm not alone. Is there anybody have any questions? Oh.
Yes.
I'm- I don't even know if they can hear me.
No, they can. There's actually.
Oh, yeah. So there's this law called Faraday's law of induction. And if you've ridden in a car, I'm sure you have. It's funny because you start the car off of a battery, but once the car's running, the battery is not doing anything. There's actually a part in your car called an alternator that is, the engine is spinning a magnet around a bunch of copper coils. And this is actually making about 18 volts, which charges your 12-volt battery and powers the rest of your car, lights, radio, all that. So this whole concept is based off of Faraday's law of induction, which literally states that the number of turns times the magnetic flux over time, the change in time will induce a voltage. So you take a magnet and you throw it through or past or by copper wires that are spooled, and it hyper excites the electrons in them and makes them move. And that's literally, so the coils, we have these coils that are rough, what is it? Roughly 130 something loops, and our little neodymium magnets, and we spin them as close to the coil as we can get it, and it makes all the electrons get excited and happy, and they just all jump one space, boom. And then every time that spins, they move faster and faster until they're all moving and just kind of spinning around the coil.
All right, Zach, we've got through the project, but you got to introduce the rest of your team because I know.
Did I not?
Yeah.
Oh, yeah, there's another, sorry, there's another slide. To be continued, right here, no. So this was originally my concept back when we did the gap analysis in NASA. When we came here, I presented it to Spear as a potential project to keep going. They liked the idea, and I've been running it since. Last year, I had the help of Aiden, Bobby, Damien, and Jake. They've all graduated. They left me, they abandoned me. I actually had the Damien, Bobby, and Aiden actually at one point when I was up in that lab for 46 hours, I reached out because they all knew SolidWorks. They were the ones that helped me CAD everything last year. So I reached out and they actually helped me kind of figure out some of the tricks, which was nice. This year I have Kayla and Caleb, who didn't make it, helping me. We've just been wrapping a lot of coils. That's so painful. Can't really get that across how much that sucks. But and then consultants, mentor, Dr. Aaron Coyner, Krystal Hopper, of course, runs like she's what we call the fearless leader. She kind of propels all of Spear forward. The engineering professor, Fraser Pruitt, yeah, huge reference whenever I have electrical engineering questions about will this work this way if I want to set it up, like the rectification I drew out and came to him. It's like, this will work. It's like, yeah. I was like, awesome. Okay. So huge reference there, consultant. Derek Morrelli has been helping me a lot. He helped me with the vapor chamber. He, like I said, he was there when I did the first tests off this new model. Max is our esports coach, and he's also got a master's in physics. So I work with him for the GD program. So I've been bouncing ideas back and forth off him, and he helps me work things out from time to time. And I think that's everybody here at the school that is contributing at the moment. So.
Thank you, Zach.
Okay.
Next up, we have our Starfall project. Searching for micrometeorite. Okay.
I've never used this thing, so give me a second. Where's my mouse? What? You said it was on here?
To the next slide. This space bar.
Oh.
Just hit the space bar.
Space bar. There we go.
Okay, there we go. I've never used this thing, as you can tell. Okay, so I'm Jillian Sork, and my project, or not my project, the SWOCC, our project, is one of them is Starfall, which is basically when we collect a bunch of micrometeorites. So what are micrometeorites? Well, they're small microscopic particles. Most of the time they're metallic and magnetic, and they're from space, and they've fallen through the Earth's atmosphere pretty much. Now when they fall, they reach really like high temperatures to a point of melting, which is kind of why most of them are spheres. The heat can turn the rocks into glass sometimes, even if it doesn't reach the same temperature. My picture has, hopefully I can see it well, but it should have some of the temperatures that they have to go through, which is why they changed that. So the types of micrometeorites, well, there's a bunch, but from what I can tell in this book, on the Trail of Stardust, I can really see two differences, which are all the ones that are magnetic and the ones that are glass. And the glass ones are the third most common, and they go through the high temperatures of about, this book says 3,600 degrees Fahrenheit, which is extremely hot. And they're not magnetic because all the nickel and all that kind of gets evaporated. So there's that, which is kind of interesting. So the purpose of this, what did I say? The purpose of our project is to pretty much keep an update on micrometeorites, like where they fall, all the different kinds, how frequent in certain places they fall. This can help teach people about the Earth's past by showing all the different materials that the Earth was originally made of, along with other planets and stuff. So our collecting and processing, it's kind of difficult, but kind of easy at the same time. It's a lot of repetitive. So mainly when we're collecting, we collect in places that run water, which include the downspouts and drains. The picture with the one on it, because I couldn't get rid of the one. That's one of the spots at the high school that we have been using. And the picture to its right is our magnet traps that we use, which are just basically really strong magnets placed in the bags so the micrometeorites don't get stuck onto the magnet. And sometimes we use even bigger, extremely big magnets, which I have right here. I don't know if you would be able to see it, but I borrowed it from the lab. It's one of these really big things. You use this, you can skim it across the ground. There's a camera over there, might as well let them see. You use it, skim it across the Earth's surface, and hopefully you collect the same things, but maybe in larger proportions because it's a bigger magnet. So our processing after collecting. So pretty much after you collect everything, you carefully put it into Petri dishes, and then pretty much what you see is all of that, and you have to search through all of that to basically find the candidates that you're looking for, like the actual micrometeorites. And then they're carefully transferred into a smaller container and sent away to a bigger facility to make sure that they're actually what we think they are. So what are we looking for? Basically, we are looking for, you look through the microscope. Gosh, I can't talk today. And you see all of that, and basically all we're looking for are the super, super small, tiny little micrometeorites. Normally they look like that. Sometimes it's harder to see with all the everything else in the way. So our findings, I've been going through all of our older stuff, so I haven't really gone to our new stuff yet. So I haven't actually found anything yet, but last year they found at least 27 candidates. And I have some at the moment, thanks to my friends at the high school, who are also doing collections there. So hopefully they have found something as well. So what's next? Well, what's next is to expand areas. Like we're always trying to expand it, get more places for traps. So like the bowling alley, and over the summer I plan on going to the beach maybe and trying to find some that way. Yeah, it's gonna be hard, but should be okay. Try and get as much stuff there, and recruiting and expanding the group, more people, it's always helpful, and it helps make the processing and finding things go a lot faster. And it also gives us more places to search because they have ideas that I don't. Okay, and this is from my friend at the high school who's doing hers on the effects of plant growth and micrometeorites. Have seen it on. I don't know much about her topic as of right now, but I will read what she has because that's what she wants. So micrometeorites fall constantly down to Earth and have been since the Earth was formed. I can't speak anymore. These micrometeorites contain nutrients. Oh my gosh. Such as magnesium and carbon that affect plants. These nutrients, thank you, this is saving me. Nutrients provided by micrometeorites can have seeded early Earth plants and would still affect plant growth and health. This experiment recreated the chemical spectrum of a typical micrometeorite as plant food and fed Wisconsin fast plants with different amounts of that food. Okay. There were two controls, a positive control which received regular liquid plant fertilizer, and a negative control which received no fertilizer or micrometeorite food. Early observations showed that although the negative control's stem length was the longest, the overall health of both the 100 years and 1,000 years variables were much better. However, as the experiment has continued, the stem length of the 100-year is the same as the stem length of the negative control. This is an ongoing experiment and not enough data has been collected yet to show significant results. So these are my references, and hopefully what some of Laura's. And thank you for listening. Okay.
So when they were saying high school student, it's actually Laura who was over at North Bend High School.
Sorry.
And when there was a couple of collection sites, that's at North Bend High School.
Yeah.
We haven't set up any over at Marshville yet. And Laura wasn't able to be with us tonight, so it's why we wanted to make sure and share her.
That's why I read everything and had
Yes,
difficulties
share
reading.
what she had to say. We're hopefully going to be able to, work some more with, possibly providing some high school internships over the summer to do some more research with some of these projects today. We've got a couple of minutes for questions if you have any for Jillian, and
I'll
then at
try
the
and
very
answer
end
them.
of the event, we'll also have another opportunity for questions.
That's as best I can. Okay, I saw this one first. Ooh. I have no idea how many we found in total.
So I think it was just the 27 from last year.
Yeah, I don't know
and
how
they're
many
not
was before that.
confirmed yet. There's, so once we're,
I'm pretty sure we have several that we haven't quite identified yet, because we still have a lot of.
We still have, I'm still going through stuff
Well,
from
there's
2022.
There's another step where we would need to send, these, samples to some of our friends in Oregon State or Portland State. We are in the process of trying to find, funding to be able to have some of those tools to be able to process these things ourselves. So that's why we can't say that we definitely confirmed anything. Those are just kind of preliminary, what we think that possibly the 27.
Okay. And I think, yes.
How distinctive are these micrometeorites compared to the other objects?
Oh, they're,
What quality?
how do they look different? Well, I don't know if I can go back.
Okay, go back.
Yeah, it's like, so the micrometeorites and, like industrial kind of stuff, sometimes they're kind of hard to figure out which is which. But,
But it looks different from this.
yeah, it looks, they both look different. You can tell which one is which. It's just when you're like first looking at it, it's kind of hard to pinpoint which one it exactly is.
A lot of times the micrometeorites are more textured and they may have pockets of like glass material,
Mhm.
whereas most of the industrial stuff is a lot smoother.
Yes. Exactly.
To be like gobstoppers where they're rings on rings on.
And so the industrial ones would just be solid metal.
For the most part.
Yes.
Okay, that. Useful, yeah.
We got one more.
I have one more. Okay.
So what is the purpose of what?
The purpose of collecting them is to basically, I think the full-on purpose is like so we can learn more about our planet and then maybe other planets. And then also like I kind of think that it's like it kind of shows our like the Earth's magnetic pole kind of thing. So like if it falls closer to like they fall closer to like the North and South Pole. So it kind of maybe shows how strong the Earth's pole is, magnetic field, something like that.
Do you want to add?
Part of it to add to it is if we can get the micrometeorites selected, there is statistical evidence that there's supposed to be about 1 micrometeorite that falls per square meter on the planet on average, but that's the average over the entire planet. So what we're trying to do within our local area is see if there are like specific regions that they happen to fall in more or in larger numbers. And then an extension to this that we're working on when we get, we have some equipment that we still need to get for it. We'd like to see the chemical composition of these to see what we can learn about essentially what the primordial solar system was like that would have spawned the micrometeorites and been part of the formation of Earth. So some of it's doing the same thing. Adding a little detail.
Yes. So, okay.
Next up, we have our ISAC program, which is our International Astronomical Search Collaboration. And we have Ian Wakeling and Ryan DeVore.
You want to stand over here? I'm not blocking it. Okay. Awesome. Hi, everybody. So as Krystal said, my name is Ian. This is Ryan. We're part of the ISAC team. I am the ISAC lead. He is my whole team right now, and I really appreciate him. So what exactly, oh, this was the slide I was supposed to have up. What exactly is ISAC? ISAC is this campaign where we're going out and we're looking at these image sets, and we're trying to find asteroids out in space. We're trying to find both previously known objects that are out there, and we're also trying to find new ones and discover new things. Now, this is not a project that's limited just here to campus. There are teams participating all over the world, and we are just one of them. But we get all of our images done every month, and we're a team that's very good about that. And these images come from the Pan-STARRS telescopes. Now, Pan-STARRS, the acronym up above me, that's the full name of it, but it's these two telescopes that are out in Hawaii that are constantly looking up at the sky and taking pictures of the different areas of the sky. What we do is then they take those pictures, they will group them into a set of 4 images, each one taken a minute apart from the previous, and they'll send them out to all the groups to go and analyze. Now, on the right is Pan-STARRS 1, and on the left is Pan-STARRS 2. We've worked with images from both, but Pan-STARRS 1 is the ones we've been working with most recently. That's the telescope that's older and it's had the worst quality images, so lucky us. Now, to actually identify these asteroids, we use a program called Astrometrica. It's this Windows 95 looking thing that we go and we boot up. And the whole reason why we use this is because there's a database inside of it that's able to actually use reference stars to find where objects should be at, and it will actually point them out for us. And then we can take these images and we can do a thing called blink them together, which I will show in a bit. So this is the program takes a look at the images. It will find reference stars, which are all of these green circles, and it will line them up, stack them on top of each other. And then we can click a button and we blink them. And what blinking them does is it will play them all the frames in a row like it's a motion picture. So we can actually take a look at this and we can see an object actually traveling between each of the 4 pictures we have. We can also take this and we can invert the colors. And this is a nice feature to have because it's a lot easier to see black marker on white than it is to see white marker on black. Now, how do we actually find this is an example of an unidentified moving object up there. You can see how that object is moving up and to the left. Those are the types of things we're looking for. Now, that is a very good example of one because it is very nice and easy to see. Most of what we find is not very nice and easy to see, as we'll get to later. Now, to actually take a look at this object and to verify whether or not it exists, the first thing we would do is we would click on the object, just in wherever it is, and this menu will pop up. And there's a lot of cool things here. There is, over here on the right, there's a lot of data. And the most important ones for us is going to be the signal to noise ratio, which is essentially how big is the object and how easy it is to see compared to the blank void around it. And we have the graph for that up there in the top right, that big curve. We also have an R value over there, which is the light intensity, how bright that object is for us to see. So what we'll do is we'll go ahead, there's a box that we click on and it'll pull up this box right here for us. This is called object identification. these are all the asteroids that it has in its system already. So we'll go through there. These two middle columns with the numbers are the declination and the right ascension of the object. And those are how far away the object is from the listed value. So what we'll do is we'll go ahead and select the object that has the closest ones to those. We'll hit OK. And we'll do that for each of our 4 images. And eventually we'll get this blue circle around our object that follows it as it travels. Also an inverted version of the image. So that's how we mark it out. And sometimes Astrometrica does not like to cooperate. While we were getting images for this slideshow, Astrometrica decided to crash. And we just thought that it was important enough that we should include it in the slide just as a silly little thing. And just to show that even though this is high-tech things that we're working with and we're looking at this stuff far away, technology is still technology and we'll run into issues every now and again. So now Ryan is going to go ahead and walk you guys through how we would find a unknown object, something that we haven't discovered yet.
So if you've done all of your things to see if it's a known object and if it's in the right spot and it doesn't show a positive for that, then we would mark it down like you would show before, but we would give it our own thing. So how we identify it, oh, did it move? Okay, so we're looking for this little teeny dot over here. And if you notice, this entire screen is about your laptop screen. So you're looking for like 1 pixel slowly moving across the objects. So this one has been labeled Coastal Oregon Research 0301. So that's would theoretically be the 301st we've found. So then you can find another unknown object and you can see that there's nothing there. So if we can get some, let me see here. So you can see that there's just barely even just a little teeny bit, and then we got to write it down. And same thing, we just do we check to see if there's anything close that could be. And then if it's not, and the signal noise ratio and the flux and everything like that is within line, we mark it down, we write down the COR, and then the number of the current find, because we're keeping track. And so if you notice that up here, the closest object to that one we chose is -5 and 0.01. 0.01 or 0.1, sorry, is pretty close. It might have been that, but the other value, it was way off on, so declination? No, anyway, doesn't matter. So one of them's way off, so it can't be that item. So we know that. So up here, we are looking at, sorry, so we mark it down as CO2 because it did not match that. And then at the end, once we found all these things, these are the known objects we found. All of these are other asteroids that would show up as red that have been found. And we will either tell them that they're off or that they are on the right thing. Because if 2 asteroids go by each other too close, they will veer off and theoretically eventually hit Earth. It's probably not going to happen, but the longer time, the longer we have to affect it. So we're not only finding new objects, we're telling them when one of them's been disturbed and it's out of where its normal orbit is. So we copied that report, we put it into a document, and then we submit them to NASA. And then it's our fearless leader over here who does all that stuff. So you can see it's an Excel thing. It tells who downloaded it, whether or not we found some. If you notice on the column right here, these are the list of the ones for this term. So as you can see, we have 2, 4, 6, 8, 9 objects we found this term. Well, actually, not just this term, this month. Because we started on the 3rd and yesterday it ended. So we followed up, we put down if you've got one, because we all have to put all of ours together. And you don't want me and him marking down different numbers for the asteroids, right? And you can't name them names. So then we report them, And then NASA will eventually get back to us and tell us whether or not we found it or not, or give us a provisional discovery. So,
Thank you, Ryan. So these are, you can stand with me. These are our results from our most recent campaign. Some of our objects that we found there at the top. Now, over the course of the last year, since I've taken over as a lead, we've had 102 objects found across 11 different campaigns. And in total, I'm assuming, since our most recent object was number 236, that we've had 236 detections throughout our lifetime. A number that didn't make it up here is also the provisional detection number, which are the objects that have not only been found by us, but have also been cited by another team, and we got credit for finding it. So those are objects that we've actually found and we've actually been credited with. And so far we are up to 3 of those objects. And what's unique about those, I should say, is that they actually take about a year to process. So even though we've only found 3, that's only back to May 2023. So we have 102 different objects that could be attributed to us going forward. Now, for participation, this is a very simple project. Anybody can get involved in it. All you need is a computer and internet in order to download your images. Now, your computer does have to be Windows or Linux running Windows through an emulator. Astrometrica doesn't like to work through Macs because Astrometrica looks like it's made in Windows 95 and it likes to crash. We also encourage student scientists a lot. In the past, we have worked with students from Brookings High School, and also currently we are working with 2 students from North Bend High School to try and get them on board and doing images and participating with us. So big thanks to these people. On the left, CJ Morgan was the previous project lead. He helped put the slideshow together originally, and this left side is all the people that have helped do images for us. And on the right is Dr. Coyner and Krystal for helping facilitate the project, getting the internships and everything, and throwing on this event. So thank you, guys. One, yes. Yeah, so this is a question I have been asked a lot recently, and I do think that it's fair that that a computer could be trained or an AI could be trained to find these sorts of things. But a big issue that I've encountered and I've had team members encounter is that we'll look at an object, and let's say there is a grain of dust flying by in the air that happened to get in the way for one of the images. An AI might actually consider that to be an object, and it will mark it as an object that's found. Even if the values don't necessarily perfectly align with what we're looking for, there's a lot of wiggle room. And so an AI might mistakenly count those as being something that was found. There's also dust that can get stuck onto the telescope, and it will actually look like it's an object, and it will move as if it was an object, but it moves in sync with the frames as they blink by, because the sky is rotating, so our images actually rotate with it, which is why we can see the objects moving. So yes, an AI could take over the job, but they would still need a human to verify that its results are accurate.
And I think I'll jump in on that. Part of the reason for this project, a lot of it is it's designed for citizen science with a fairly low bar to entry. So a lot of the, even though it could be done with AI or with some complicated machine learning, a lot of times they want to try to get younger scientists involved. So a lot of the teams have high school students, have middle school students, have community college students on them that are essentially getting their foot in the door for astronomical measurements and observations. So it's kind of the idea behind the project is to keep it as user friendly as possible.
You got to remember that NASA's found all the low hanging fruit. We're looking for the little teeny guys out in the middle of nowhere that nobody can see. And I'm a lot cheaper since I work for, pats on the head than a NASA researcher. So
I think this would be challenging for a lot of you guys.
it would be. Yeah.
Thank you, Ian and Ryan.
Yeah.
Thanks for the.
Yeah, it's always exciting to hear about the different, I like when you ask those types of questions, Nick, on the AI, because there is a lot of possibility for that, but what I like is seeing this, collaboration of people working on things and getting an international collaboration. That's exactly what that is. Okay. Next, we have Devin Carter for time of flight analysis. And Devin's actually been working with both Dr. Coyner and Dr. Roman Gomez. Dr. Gomez is from Southwest Research Institute in San Antonio. So here we go.
That said, I haven't actually had any personal contact with Dr. Gomez. It's all been through Dr. Coyner. So, hi.
We have spare people at this point.
Fair. That's not fun. Like she said, I'm Devin Carter. I'm a computer science student going for a transfer degree. So, looking at this, I think what many of you may be asking yourself is, what is a pickup ion? Now, space isn't the bad. Space is full of stuff. Am I still on the camera? It's pointing here, isn't it?
Yes.
Okay, cool. Space is full of stuff. Not as much stuff as we have down here, little atoms here and there, all neutrally charged, no ions generally. Not all. I won't make sweeping generalizations. Mostly neutrally charged atoms, helium, hydrogen, oxygen, yada, yada. When these atoms are under the influence of a solar wind, they will gain ionizing, they will be ionized and carried along by that solar wind. And just sort of jettison off into space along that path. Now, the magnetospheric multiscalar mission is a mission by NASA wherein there are 4 satellites that have been put out into orbit and are used to collect various data on magnetic resonances, pick up ions, and I was looking at the list of instruments they use earlier, but it's so much. However, we're only worried about the pickup ions, which is one tiny little part of it. Now, if you look at this, I was expecting a much smaller screen so I could sort of wave there. If you look at this, this is sort of the region of space that we're trying to get information from, around where the satellites are. We're looking at the solar winds coming in, all that, sorry. All the planning in the world and nerves get in the way, right? Thank you. Okay, so getting the pickup ions from solar winds, and this is the data that we receive. It's transcribed by NASA into their website that we gather from. It's a lot of lines, so many lines. But just to simplify, again, I was really expecting a smaller screen. So if you look right down this line, this is the perfect set of data. Well, perfect, again, not making sweeping generalizations. This is an excellent set of data. What we're looking for is, generally speaking, even across these lines, so we're not getting a lot of fluctuations. And in that top one, we don't want, you see that chunk just to the right of where I was pointing? We don't want things like that. We want sort of sparse, not a lot of noise. Like that. That's an example of terrible data that we don't want to be part of. This is, I think it was 12 days after that one. So generally speaking, this is very close together. And this generally means that we either have interference from the Earth's magnetosphere, or I don't know what else is in space. There's so much things, so many things in space. But if you look up there, you'll see this kind of looks all right. But then you come down to here and all of this information is muddled and fluctuating, like I said earlier. So currently we're in early stages on data collection, and we haven't had many findings yet. This is pickup research from CJ, who was mentioned in the last presentation. And sorry. we're planning on having findings to present in October, and I should have put a slide on this. So basically what we're looking at is the December months where the Earth is in the, what was it?
The helium focus.
Helium focusing cone, yes. I could think of focusing cone, helium wasn't coming to mind. Helium focusing cone of the sun, which is essentially as the sun is moving through space, you know, orbiting the Milky Way, it's sending out these pickup ions, and the path that it leaves has a much higher concentration of pickup ions. So as we are in these winter months, we're crossing the helium focusing cone, and what we intend to do is use the data that we find in order to sort of model out where in the path we are and where the sun is moving, essentially. In the future, after having our data or having our findings in October, we're hoping to automate the process a little bit more, working on some code in C++, as well as some Python to sort of make a web service and collect the data better, easier, and without too much human grunt work. I'd like to give thanks to my mentor, Dr. Aaron Coyner, Saman, who's right over there. He's my team member, single team member. CJ, as I mentioned, Dr. Roman Gomez, and Joey, how did you pronounce it again?
Joey
Mukherjee, who is in charge of the systems that we are pulling the data from, making sure that they're still up and running.
He is our resident data miner on the screen.
Yes. Oh, I thought I had a question slide. If there are any questions?
Is there like a NASA?
Yeah,
API?
sorry, there are a NASA.
Are you using an API? NASA?
They have a website that we go on to and collect it from.
You click and download a batch of data?
Yes,
Yeah.
Okay.
and we download it as a text file.
It's set up through SWRI, because Southwest Research is actually in charge of the hot plasma compositional analyzer instrument where we get the data from. And they essentially have a GUI interface that we can pick days and we can go through essentially their overview data, and then we can look at specific things like looking for hydrogen fluxes, looking for helium fluxes that we go through on each day, and then try to process the flux values and look for where the flux cones happen and as compared to just a normal day worth of data.
Just
We
pretend I said
usually
that.
try to do chunks of about an hour at a time, because if I do any more than about 2 hours at a time, I get a phone call from Joey going, "You tried to break my machine."
So I understood this because, for NOAA, for example, which might be similar to NASA in some ways, they have data that can be downloaded like in an Excel, for example, a text file, sea level, for example, with water temperature. But if you send instructions directly from some sort of other script, like a Python script that's running, you actually don't have to go through the web browser, click through it. You could, in theory, have that be part of your automated workflow.
And that's actually part of what I mentioned about the Python script, that's part of the plan to do.
So you'll
Yeah.
already.
Yes, I may not have verbalized it well, but that is part of the plan, yes. No, don't take it back. Thank you. Anyone else? Okay.
Next up, we have Jack Davis with Monarchs of the Shoreline, Statistical Analysis of the Frequency of King Tides. For the longest time, we would just say the King Tides Project, and now it has a beautiful title, so thank you. This is a pointer he just,
Okay.
there you go.
Alrighty, hello everyone. My name is Jack Davis, as Krystal said, and today we're gonna be looking at the monarchs of the shoreline, or as most people call them, king tides. Specifically, we're gonna be looking at the frequency of king tides on the Oregon coast, specifically from the Port Orford station down the coast from us. So what are king tides? King tides are tides that are extremely high and may occur in the winter months and during new or full moons in winter months. Sometimes, occasionally in the spring and fall they occur too, but it's mainly winter months. The scientific definition is a tide that is 3 standard deviations above the mean water level for that year. And the standard deviation, that's just the standard deviation is a measure of the variation for a set of data. So from whatever your data set is, it gives you this bell curve for that. So why did I choose king tides? Coming from little landlocked Saskatchewan in Canada, oceans have always fascinated me and piqued my interest. So when I came to SWOCC and I joined the SPEAR team, I saw they had a research project that was looking at tides for the ocean, and I was like, I want to be a part of that. So I tried to join the team and I did, but lo and behold, there was no one else on the team and I was left all by myself to do it. So starting out, I didn't have anyone to talk to and work it off. So it was just me and Dr. Coyner working side by side for the first little bit. And the first thought we had was we could go to the National Oceanic and Atmospheric Administration website, otherwise known as NOAA, and create a web scraping code to go through and get all the data we needed and go through that way. But that didn't really work. So then we decided we could try visual point data to calculate the tides, but this just didn't seem to be working either. It would have been taking too much time and only focus on present to future tide data, since we'd have to take a picture of every tide, take a GPS calculation, and mark each peak of the tide to see when it reached its highest point. So then we decided to take photos and just use them as visual aids for future presentations like this. So, and all the photos included in here are taken by myself. And then so for our final ideas, me and Nick worked very closely on this. Nick is in the crowd right there. Give everyone a wave, Nick. There you go. So we used data from the NOAA website, which we exported in CSV files, as that was the easiest way we could export it and make it easy to read and easy to work with in Python code. And then we still use the visual aids with pictures. So there's another picture we took. And that was our final idea and where we started and started building up from there. So then we started coding. This was a process, to say the least. It started out with just writing code to read the CSV charts month by month, which this is some of it. This isn't all of it, but it's for the most part what we used. And this code, we ran it through here. It spit out a graph and it spit out the date, time, predicted water level, average water level, and there was one more, verified water level for the height it came out at. And with that, we then were able to put that data into a chart or into another set of code, which ran a bunch of calculations to find standard deviation, mean, and we ran those numbers through another code, which gave us just the high tides that were above what we wanted it to be and the times that were associated with each of those water levels. And then this is our chart from March 2023 to February 2024, from when we started it to when we started it in February pretty much. We started coding and then we went back a whole year to March. And so this side, our y-axis showing us the amplitude of the weight of the tides at given times. And at 8.4 feet, that's when we had constituted a king tide for the previous year. And then across the bottom here with these massive numbers is the arrival time in minutes. So each 100,000 minutes for every point on the x-axis. And then this was the code that Nick worked on. It was a peak detector code. So these green lines on here show each trough when there would be a low water level time, and each purple line shows a high tide. So we could see which time space they ended up with and where they were in relation to each other and how often they occurred within one another. Our future plans are to expand the project to have more data in the past and the future, so we can get a bigger pool of data and see if there's been a trend with king tides happening more frequently or happening less often as time's gone on. And then we're gonna also look at other factors that influence the role of king tides, whether it be coastline shape, coastline depth, atmospheric pressure, or solar activity. There's no data on that right now, so we want to try and see if we can find something out that no one has tried to do research on in the past. A special thanks to Oregon Space Grant Consortium and the Oregon Internship Opportunity Network for funding my project, and thanks to Dr. Coyner and Nick for working so closely with me on this project. Any questions? Yes, Amy.
Is there any data that you could pull about swell? So the swell of the ocean, because that potentially could impact the data that you're getting.
Right now, I've been trying to find something for that, but I haven't been able to find any data on that yet. But I'm gonna try and find something in the
Okay, I
future.
could probably point you in some directions.
Okay. Any other questions? All right, thank you for your time. Oh, one more? Oh, yes.
So you do reports about like, oh, there's gonna be a king tide. Are there more or less actual king tides than what a lot of the predictions are?
So this chart is a great image. So this isn't in order from March to February. It got messed up when we were combining all the CSV files. So each king tide, they only constitute them if they're over like 8.9 feet when I ran through the sheets, and it showed like 8.9. So everything here is still a king tide below the 8.9 is still a king tide, but they don't report it because it's not as impactful as the ones that are 9+ feet above the average. Yes. That's probably some of them you could, some of them probably not.
Can I answer? Sorry. So a common misconception that people have is that king tides bring in really big waves, and that's actually a misconception. So it's the swell that brings in the large surf and waves that could take you out. So when you have combined big swells with big king tides, that's when you get the huge events at Lake Shore Acres and stuff. So a lot of times people from inland will drive out to the coast during king tides, but the swell is like a 1-foot swell, and they're very disappointed because they came for the king tides, when really what they're looking for is the giant swell, which also happens during the winter. So,
Does it affect
surfing? Yeah. Does it affect surfing? Yes, it does. We love big swells, king tides sometimes.
All right, thank you.
So I've been monitoring the questions online as well. So those of you online, if you have any questions, please let us know and we'll pass it on. It's always nice to have all of the professors around during our weekly check-in with the team. By the way, we meet on Mondays at 2 in the physics lab, if anybody's interested. We have a group of the professors that are always kind of on hand, and maybe it's something that physics and engineering can help with, or chemistry, or just now, like with biology, geology. And so I love the collaboration of all the different departments working together on this. But we have found, somebody working on something, you wouldn't think that this, that maybe the chemistry professors like, jumping in with mango, and it really, really helps. So next up, we have an academic review of nuclear propulsion with Cameron Miller.
All right. So I got to do a research review with STAR, which is a student academic research review program, which is related with NASA. And their pitch was basically, it has to be you have to do something kind of related to NASA goals, but do whatever you want. People have done all sorts of things like women's health in space, or someone the year before me did it on RTGs, which are radioactive thermal generators for spacecraft. And me, I want to be a nuclear engineer. And I don't get a lot of opportunities to have personal projects with that, typically frowned upon. So I immediately jumped at the chance to do something like this. And I'm really happy with what I was able to find. So the atomic rocket, right? After we created nuclear bombs, we had this vision of a future right? A miraculous world where we'd use atomic energy not as weapons, but as an unlimited source of power. Like science fiction showed us reaching for the stars, conquering alien worlds with our atomic rockets to lift us there, right? But as we now know, right, living 70 years later, we didn't really end up seeing that. So my question was, what happened to these like ideas that we had, this vision for the future that we had? So I started looking into nuclear propulsion technology, which envelops kind of anything that involves using nuclear power to help make thrust. So technically, like submarines and aircraft carriers, we have already do that. But for space, we face a whole bunch of new challenges, right? We don't have the water to help move us along. Everything we have to move has to come with us. And the idea for this is as old as the atomic bomb. While the scientists were working on the Manhattan Project at Los Alamos National Laboratory, they were thinking of ways to use the research they were making for something other than untold destruction that would kill hundreds of thousands of people, right? And so these papers would come out over time, and we would see a lot of different variations because there's more than one way to use nuclear technology to help with space travel. And in my paper, I went over 3 of the pretty significant ones. Starting with what's the most similar to what we have nuclear thermal propulsion. So this is about as similar to our standard rockets as you get. So with what we use right now, chemical rockets, they take some really like light propellant and burn it to push out really hot gas as fast as they can, right? And what makes them more efficient is trying to get as light of a gas as you can, right? You want to take up as little as you can with you because all the more weight you bring means you have to pull more of it up, right? And they get about, like their average atomic size was about 8 roughly, and you can get a specific impulse, which is a measurement of the force that you can put out per second, of about 450. Nuclear thermal kind of replaces the chemical reactions to heat that gas with a sustained nuclear power to create heat a lot more efficiently. And through what we found on some of the different types we could have, we saw vast potential improvements over chemical. So if chemical could produce a specific impulse of about 450 pounds of thrust per second, nuclear could go from anywhere from 850 up to 2,500, right? A drastic increase in efficiency. And this is, as far as this is concerned, a relatively simple change, right? Just changing how we do our main chemical rocket boosters. But it goes even deeper. There are other ways, such as nuclear electric propulsion. This is where we get a bit more complicated. So this one, instead of using nuclear power to heat up our propellant gas, we're using it to create ions, which we then shoot out as a propellant, right? Ions are really light, so this isn't the strongest form of propulsion, but it helps us reach so much farther and is useful after, like this is something you'd see on the main big rocket boosters. This is what you see after the craft is already in space and needs to do positional movement, right? So with this, it really can extend how far we can reach. We already have some ideas for electric propulsion using solar panels, right? But as we go farther from our sun, we get less and less power from that to the point where we can't really use them anymore. But bringing a nuclear reactor with us means we can keep producing that energy constantly, which could be our best bet for reaching towards the stars. And finally, the most abstract form of power we have, which kind of redesigns how we even travel in space, is nuclear pulse propulsion. It's, from what my diagrams show up here, it's about as simple as using a nuclear bomb to push your spaceship, which, though it sounds absolutely insane, it's probably the biggest potential out of any of the 3 for efficiency, right? So there's a couple different designs that were theorized and experimented with, right? You have on the top left here, we have external pulse. You shoot the bomb outside of your ship and it pushes it. You have the internal pulse version where you have it contained in an explosion chamber. So the bomb comes with you, but this was seen as a lot less efficient. One of the main things about this design is that it would have a inertial dampener on here, right? So it's not like you're getting hit with a car crash amount of force when the bomb goes off, sort of like a shock absorber on your car, right? To change the force to something where any people in there wouldn't get turned into meat. And they were designing all sorts of really efficient ways to make as like efficient of a nuclear device as you could, right? In the void of space, they would add, like on the right here, we see a diagram of one of these designed fuel canisters, where they would add this beryllium oxide to the bomb, and that would act as a barrier, right? That would be the wind that would go into this proverbial sails of our craft. But so with all these really big potential ideas, right? Why don't we have this today? Why did we just kind of abandon it and give up? Did we kind of hit a limit? Or did we find it wasn't as good as we say? Well, not really. So the Cold War happened right after World War II. And as tensions rose, we got really, really scared about being seen as developing new weapons, right? Especially with nuclear pulse, right? The idea of putting up a spacecraft that can shoot miniature nuclear bombs wasn't really popular with the United Nations. So a lot of the research that was going into this, unfortunately, had to be shut down to avoid greater escalation in the war. Right, but now we aren't in the Cold War anymore. The Soviet Union doesn't exist. And we have the potential to go back to this, right? One of the main things I had to do with this is align this with NASA's goals and with the upcoming Artemis program, where we're looking to go back to the moon and go to Mars. What would make that easier than better engines on our spacecraft, right? That lets us get there faster, bring more stuff with us, right? Makes everything easier. And we have designs for this. As recently as 2021, NASA released a compass study about, okay, so let's in theory try to make like the cheapest, most efficient way to go to Mars. And they ended up using a combination, creating this theoretical vehicle, which uses a combination of nuclear thermal and nuclear electric propulsion. And they like designed the entire thing down to all the subsystems and the timelines. Like we could see a manned Mars mission by the 2030s, even the early 2040s, right? So this is possible. And on their reports, they list one of the main things that's holding them back, not as the technology, right? Not as the limitations, but by the lack of research and development we've had on this over the past decades with everything having been cut, right? And I know that nuclear technology doesn't really inspire a vote of confidence, right? It brings images of Hiroshima, Nagasaki, Chernobyl, 3 Mile Island, Fukushima, right? It's been devastating throughout our history. But I think of it kind of like obsidian, where you can easily chip obsidian to make a sharp arrow point, which lets you kill things easier, right? But if you put that in the hands of a professional, right, chip that down into a fine scalpel and give it to somebody with the knowledge of what they're doing, and they can perform miracles, right? We have so much potential with this, and I would really love to see more about that. But yeah, in my paper, I wasn't allowed to kind of sales pitch it, but I'm out of paper now, so I get to be biased. Tell you how much I like this. So yeah, thank you.
I'll tee one up for you, Karen. What was the most interesting thing you found in doing? Because I know most of your academic research part of this was looking at the work that had been done prior and kind of trying to synthesize it all. What was the most interesting thing that you found in going through your various sources?
It was definitely interesting having the opportunity to read the official Los Alamos papers, right? That's where it's got its start. So reading the same papers that they were writing while they were making the atomic bomb, these declassified files, that was pretty cool. But definitely nuclear pulse propulsion surprised me the most. The idea of let's use a bomb to shoot our craft into space sounds like something I would have thought of when I was like a kindergartner. That would not have been a great idea. But to think that not only is it feasible, but in theory, it's probably the best option we have. It's incredible to me.
So, you said you went to NASA. How did you do that?
I went to NASA. Well, I went through all their web.
I
So
mean, your research, how did you get there?
So looking at NASA's priorities that they have listed, they have every 4 years and the most recent one was 2022. They released their sort of strategic directives of like, okay, where do we want to be going the next couple of years? And looking over that, right, with the Artemis program coming up, and even on there, they had listed that they want to do more research and development into some different technologies for nuclear thermal propulsion. So it was pretty nice seeing that, oh, so this is something that isn't like coming out of the blue. This is something that they are interested in. Yeah.
Follow-on question.
Mhm.
That was very interesting, but what I was meaning is,
Oh.
how did you find out about the opportunity?
Oh, the opportunity. I have a lot of classes with Dr. Coyner because I'm an engineering student, and Dr. Coyner loves to give us all this information on upcoming opportunities relating to STEM stuff and stuff with Spear. And so I found out through him. And so since I have 3 different classes with him, I got the pitch 3 different times. So I had the chance to think, maybe I should do something on this. Yeah.
I think that you'll see it used in space rather than kind of taking off from the Earth.
Oh, definitely. This is something that you'd want to use a lot more in space. On some of the reports, they talked about the potential for radioactive contamination. And on one of the reports for nuclear thermal, they estimated that doing a launch in atmosphere, every launch would pollute to the point where it could kill 5 people, is what they said. So this is obviously something you don't want to be using in atmosphere, a lot of this stuff. But some of the other technologies are definitely a lot more viable. And this was from their very early work with the less efficient, more polluting variants. But it's something that we have to look into more to see if we could end up in a place where we could like have a launch without a detrimental amount of radioactive contamination.
Question. So this is all fusion, right? Have you seen any of the stuff for fission, and how would it change your?
So fission is a lot of what's integrated into this. All of the thermal and most of the electric ideas are based off of fission detonations and fission power, because fission is what we use for almost all of our nuclear power today, right? We're still trying to research fusion to find a sustainable way to do it. But with what we know, fission is our best bet for most of these programs. And like fission is what we would use for the nuclear pulses, right? And people thought of it as maybe like a swords to plowshare kind of thing, where we could repurpose some of the established global nuclear arsenal to something that's more positive. Yeah.
Right. Next up, we have investigations into the Yahats basalt. Michael Stone.
All right. Hello, everyone. I'm Michael Stone. Yes, that is my real name. I'm a geology major. And I did my research project on the Yahats basalt and trying to figure out how it might relate to the origins of the Yellowstone hotspot mantle plume kind of thing. But you might be asking, what is the Yahats basalt rather? Yahats basalt is a series of basaltic mafic rocks in central Oregon on the Siletz River accreted terrain. But it's associated with mainly superficial high silica basalt flows and breccias and dikes that were formed between 36 and 34 million years ago. And the formation of the Yahats basalt is commonly debated, but it is generally accepted that it was formed in a similar environment as the Yellowstone hotspot might have originated in, because it has been theorized to have been caused by a mantle plume as it subducted under the oceanic plate Juan Fuca and transferred over to the North American plate, and then moved on from there over to where Yellowstone currently is right now. But yeah, and this is ongoing research, so I don't have a whole lot of data on it at the moment, but I am planning on getting a little more of that later as soon as some samples are getting processed from study areas that I've collected from, such as the Strawberry Hill Smelt Sands Recreation Site and Hestia Head. These are the main areas that the Yachats basalt is visible. Pretty much the only sites except for like a quarry over by a little north of Yachats. But two of these images actually have the dikes that are associated with the Yachats basalt, which may or may not actually be the Yachats basalt, but for sure the Smelt Sands Recreation Site pictured in the middle, like the kind of rocks there, are the basalts that don't have any dikes on it, but yeah. The dikes themselves, though, aren't necessarily the same as the Yachats basalt because they are younger and might be from the Cascade Head basalt, which is more northward and also younger, and it more closely matches the chemistry of that area as well. And oh man, it's kind of hard to see. But I got Google image pictures for where the dikes are located on Strawberry Hill and Hesita Head. They're way more prevalent in the Strawberry Hill region because, well, that's still debated. I'm not entirely sure about that one. But Hesita Head is theorized to be the main area where a lot of the volcanism for the Yachats basalt may have started and where all that kind of sprayed up through the crust and then out northward from there. But how it connects to the Yellowstone hotspot, there are three different projected paths for where the Yellowstone hotspot might have kind of followed. Yachats basalt being one of them as the Y of 36 million years ago, southward, or wait, no, I think it's a T, but yeah, this is a weird diagram. The blue picture here is the Siletz River terrain, like a concreted terrain, which is also theorized to be from the Yellowstone hotspot, creating island arcs right off the Juan de Fuca Ridge, and then like being scraped onto the surface of the North American plate from there, and then after which all the volcanism, like the Yachats basalt, formed through, and then got pushed northward because of the clockwise rotation of the North American plate. And then also because of the North American plate clockwise rotation, the Yellowstone hotspot stayed still, but the North American plate moved over it. So over 80 million years, it got to where it is now. And a lot of the chemistry is a little different because it has collected some different material from the crust as it moved through the North American plate, and so that makes it a little tricky to figure out the exact comparison between the Yachats and Yellowstone basalt, but I am trying to work on getting more chemical analysis done on that. I had a thank you portion and a question portion, but apparently that's not on here. It's all right. So yeah, so further research for that will have to include more chemical analysis of not only the Yellowstone, the Yachats basalt, keep messing that up, but also other volcanism spots along the Siletz River terrain, and try and compare that to some of the other chemistry from the Yellowstone hotspot associated magnetism sites itself. But until then, that's all that I got. And any questions? Yes.
When you're doing chemical analysis, what are the things you look for?
Well, I'm looking for more of a general comparison, but also in one of the papers I found, there is less lead in the Yachats basalt compared to the Yellowstone. So I'm trying to get a better comparison of that. Also, a little bit more of the minerals that might be associated with both of them that might have stayed over the course of the 40 million years that it's been on the North American plate. Planning on doing maybe XRF, maybe a little bit of thin section analysis on that. Just, yeah, just comparison.
Selling yourself a little short on this. One of the things Michael's also doing is looking at hand samples. So what do they look like in terms of how large individual mineral crystals are growing? So it's sort of like a fingerprint for different places that produce basalt and seeing if we can match them. So the thin sections, like you identify tiny minerals that you can't see with the naked eye, and the other forms of geochemical analysis we can do are looking for sort of ratios of different elements as a fingerprint for where did it come from.
Yeah, it's hard to compare like how much magnesium to how much magnesium, but a ratio of like thorium to osmium is more reliable. When it's two elements that crash together, even if you melt it or freeze it and melt it and freeze it, if it comes from the same thing, the ratio of those two that track together will still be the same. So it's ratios of rare metals.
Yes, and it's also harder to figure out direct comparisons with the materials though, because a lot of contaminants it picked up from like the Yellowstone hotspot picked up a lot more contaminants as it moved over. So it's hard to get a direct comparison, but we can get a general idea of like what it's made out of compared to the Yachats.
Another neat thing about this event is that it kind of shows you the wide array of different things happening right here. We have a lot of really amazing students that are interested in a variety of different things, and being able to have the community provide, you know, a facility like this is just amazing for this work to kind of continue. Here in a little bit, you'll also learn a little bit more about a recent event that Michael actually attended presenting this work. He did an awesome job up in Washington and Spokane. Next up, we have, here we go. All right, we have Caleb Laframboise, one of our biology students, and Michelle Riley is an agroecology student. They are going to talk to us a little bit about green crabs. And if you were lucky enough to be at their presentation recently, just about a week ago, they had a big presentation on this and even brought us some live crabs. So thank you. Here you go.
Right, so thank you, Krystal. So I'm Caleb. This is Michelle. Technically, we're not really part of SPEAR, but we're lucky enough to get invited to this and share a little bit about what we've been working on. So we both have been working at an internship at SWOCC. And we've been working with green crabs. So basically, green crabs are just a very destructive invasive species that came over from Europe. They first got to the East Coast in the early 1800s. And then they eventually made their way here, and we started monitoring them in Coos Bay in 1998. So some of the reasons that they're so destructive is because they're very destructive to eelgrass beds. They like to dig them up. They like to eat the rhizomes, which are the root of the eelgrass. And eelgrass is very, very important just to help preventing erosion, giving habitat just to a lot of different animals. And then, what? Is there something you wanted to add? Oh, okay. And then another thing they do is they just eat all sorts of native bivalves, so clams, mussels, oysters, and they also eat a lot of our native shellfish, especially the baby Dungeness crabs. So yeah, they're very, very destructive.
So how do you identify these crabs? If you're very familiar with crabs, if you go crabbing a lot, you probably will be able to identify them pretty well. They look very different from Dungeness or red rock crabs. Usually they have sort of a muddy brownish green color on the back, and then if you flip them over, they're gonna vary in in colors. So it could be green, even red, orange, yellow, or a cream color. And they're fairly small, around 2 to 4 inches on average. So green crabs have very valuable uses, and at the top of its value is its culinary use. So as you probably know, crab is pretty expensive, especially soft shell crab. And what we're trying to find is a consistency in data for the green crab's molting period on the West Coast, so that we can get that information and give it out to anyone on the coast. Maybe they want to start up a soft shell crab industry. And other uses is maybe for your garden or even for your chickens. So they are very nutritious, has this important nutrients for your garden, and you can just feed them to your chickens. And yeah, so to control their numbers and to take advantage of their population size, these are some ways you can go out there, trap them, and use them.
Yeah, so as Michelle was saying, kind of the best thing anyone can do to help is go out and trap them and use them for yourself, whether you want to eat them, or like she was saying, use them for fertilizer, or if you have chickens or any animals, you can feed them to those. So for trapping the green crabs, usually like popular places to go trapping are like the Charleston Boat Basin, or even kind of down in Empire. But typically you won't find many green crabs there. They like to sit higher up in the estuary, away from the adult red rock crabs or Dungeness crabs who can actually eat them. So we have a little map of some of our places we trap over here. The main place we go is the Cruise History Museum. There's a little area out front, and that's just where we get the most crabs. So we also have different types of traps we use. So typically traps that you'd use for Dungeness or red rock have very big kind of holes in between the rope that hold the crabs in, just so the smaller crabs can get out. And oftentimes the green crabs, if you do get one, they'll fall through those. But we actually did try using just a regular crab trap, and we were able to still get some green crabs. So it can actually be helpful then just to weed out the really, really small green crabs that it's not really worth keeping to eat. And then another style, I wish we had a picture, but it's called the Fukui trap. It's kind of like your typical crab trap, but the netting is just much smaller. And then you can also use minnow traps, which are just a little cylinder with 2 openings on the end. And then the last type is a shrimp trap, which again is just kind of like a big, when you think of a crab pot, just very small netting. And then one thing to add, just the easiest way to identify them is by their spines. So this picture up here, they just have 5 spines on each side of the eye. And then, I can actually use the mouse. So there's 5 spines on each side of the eyes, and then 3 little bumps in the middle. So that's just the easiest telltale sign to identify them, because they can change a bit in color throughout their life.
And something to also add, our internship was very self-directed. Our internship boss was like, just gave us a bunch of information and was like, do whatever you want, basically, along some lines. And so we did a series of experiments. One of my experiments was a a taste test to see if people actually liked the green crab. So I did a blind taste test to 20 teachers and students, and I fed them green crab and Dungeness crab and asked them to rate each one out of 10 and see if they could guess which one was which, basically. And I got some very surprising results. I got actually a higher rating for the green crab than the Dungeness crab. It was like 7.8 out of 10 for the green crab and 7.3 out of 10 for the Dungeness. So it was pretty close, but it's higher. So yeah, I would say it tastes more like a red rock crab, softer and sweeter. And then another experiment we did was chicken versus tuna for bait. So we wanted to find more information on just trapping so that you guys or anyone would be interested in knowing how to trap, what bait they like to, what bait attracts them. And we found that chicken by far like attracted more crabs. Any other experience? Yeah, so also something about the trapping, they sit higher in the estuary and closer to the rocks. So if you do want to go trap, you don't want to be throwing your traps deep into the water off of a dock. You want to set them just along the rocks and they'll come up and go into the traps. And there are ways to change the way you're like put netting in a regular crab trap so that the crabs don't fall through. So you could DIY it, basically. So yeah. Yeah, that's basically it. Yes, Nick.
What kind of crab trap, like, kind of, I don't know what the kinds are, but what kind of like the size or whatever should someone get? This trap.
So the best trap would be a fukui trap. They are pretty small. I would say they're like 2-inch holes in the spacing so that nothing can get out, really. We
Like slightly smaller.
Yeah. The fukui traps are, yeah, pretty small and they're a lot cheaper. So if you specifically want traps just to catch green crabs, yeah. Yeah, Saman?
So I went out there to try to catch crab. How many can you catch? Let's say 5 or 6 hours.
Yeah.
Yeah. So the way we do it is we go at low tide, we set up the traps and stake them into the water and we come back the next day at low tide. And with that, in 8 traps, we're getting over like 100 crabs, like averaging 20 some crabs per trap. So within that time, you should be able to get plenty. The limit right now is 35, just because ODFW doesn't want people misidentifying them and then just taking a bunch of native crabs. So within a few hours, you should be able to get probably around the limit.
And not to promote illegal behavior, but no one's checking at these spots. Yeah. Yes, Brian.
I noticed, you mentioned that you only did the Dungeness, and it's supposed to be the best crab bait in the world, and they did better. So that's pretty good.
I mean,
for your research.
I've heard that king crab is the best.
Yeah, it sells for most, but for taste, they say Dungeness. But anyway, but did you read by any chance versus green crab?
No, I did not. It was already kind of hard to find people who was willing to eat crab from me.
And I think the taste is pretty subjective. I've had people like say they don't like it, like they think the green crab's disgusting and regular crab is like okay, just because the green crab is sweeter, and for some people that kind of puts them off.
It also kind of tastes more like the ocean, in my opinion. It definitely has a stronger flavor. Yeah.
Question about the methodology. Did you always do like the best followed by green crab, or green crab followed by best?
I did. I always, just because I thought that if someone tasted the Dungeness, because it's very like, it's just crab. But then, oh, this, and then you taste the other one. This crab tastes different. So I always did the Dungeness first. Yeah.
Want to say thank you to Dr. Sean Schooler with the South Slough National Estuary for helping with the internship of these students. And I was really excited to connect with them not long ago. And so it was exciting to be able to have you guys present. And then thank you for joining ours. And yes, you guys are not technically with Spear, but no, if you everybody's welcome to come to Spear at any moment, and you can say you're part of Spear. So it's more of kind of a place that we're just supporting all types of research going on here. So next up, we actually have our geology professor, Dr. Wynn McLaughlin.
Obviously not a student. So this is more of showing off another project that a couple students are working on and that we're looking for a bunch more people to work on. So I know we don't have very many of you that are new, fresh blood, but like come to the dark side, work on the rocks. So this is an abbreviated version of a talk I just gave at Geological Society of America, where Michael also presented a poster. And I'm trying to look into one of our local geology sites, so Fossil Point. And this is a site that we take students to on several of our field trips, as well as even within kind of the sphere of lab, because this is really, really close to campus. In fact, if you have driven in towards Charleston and past the Dairy Queen at the edge of Coos Bay, right after the Dairy Queen, when you can see the ocean, there's a little gravel pullout, and that's where Fossil Point is. It was originally named in 1896. And this sort of heavily implies that in the 1800s, somebody must have found fossils, or presumably they wouldn't have named it Fossil Point. The first map that it appears on, where it's marked right there with Fossil Point, is from a 1901 map that was looking at geologic resources in Coos County. So specifically, this was a map trying to figure out where there were coal deposits locally. Fossils were noted, but they were the wrong kind of fossils to be associated with resources. So it doesn't appear again until some later publications from the 1920s and 1930s. However, as we start jumping into these later publications, one of the first things I noticed is exactly where Fossil Point is on the map seems to change quite a bit. Roughly this entire stretch along the coastline here, sort of in between Empire and getting down into Barview, it's all really the same rocks. So it's kind of bouncing around what gets called Fossil Point. Now, why do we care about Fossil Point? Obviously, I'm a little biased as a paleontologist, but I'm really interested in some of the fossils that are coming out of it. One of the most common fossils that admittedly doesn't look all that exciting is this that's called teredo wood. So this is fossil wood that is still woody material that had little tiny clams and various things burrow little holes into it. So while it looks like just an abstract design, this is a really neat opportunity within paleontology that we're actually seeing behavior of animals. So what kind of environment this was like, what sort of creatures were there, what were they doing? Most of the lowest down rocks at Fossil Point, the oldest ones, are famous for having tons and tons and tons of scallop fossils. If you go down the coast a little bit, there are commonly collected fossils that get called Bandon biscuits that are fossil scallops. We have a ton of them here in Coos Bay as well. If they are loose floating around, they are totally legal and free to collect, and I find them every single time I go, so they are there if you want to go collect really cool fossils. There are also larger things coming out of Fossil Point, though, like whales. Here's one of the little scallops. They range up to about dinner plate size for some of them. The whales have been known since at least the 1920s, and I suspect this may even involve that 1800s description. So they found fossil bone. This has been noted for a long time, and then kind of nothing has really been done with it. In 2007, the North American Research Group for amateurs doing paleontology on primarily the West Coast helped collect a fossil whale skull. And it was affectionately given the name Wally the whale. This was really quite a big endeavor since you can only go out there at low tide. So at low tide, they had to remove a really lot of super, super hard rock, put plaster to protect the skull around this big whale skull, and then move a many hundreds of pound rock. The catch on fossils, though, is when you go see a really cool skeleton in a museum, that took probably hundreds to thousands of hours of somebody working in a laboratory, cleaning off tiny little bits of rock, and then gluing the pieces you inevitably break back on. The catch on Wally is sitting over at the Charleston Marine Center and has never been removed from that plaster case. One of the things I would really like some students to be interested in is I now have the equipment to be able to work on removing Wally from the rock. So we need to prepare Wally so we can see more of the characteristics and figure out what kind of whale Wally is. Wally is a great name, but it would be really fun to have a scientific name of what sort of whale was living there. There's also a lot of new fossils coming out of it. As I said, every single time I go to Fossil Point, I find something cool and new. There's things like lots of little mammal bones coming out. So this is a piece of a backbone, and it is the growth plate that's showing. So this was like a baby dolphin. Really cool, maybe kind of sad. We also have been getting some fossil sea urchins for the first time. So new fossils that are not described to science. If students want to work on this, you potentially have the possibility of naming new species. That happens a lot more than people think in paleontology. Now, what was really interesting to me as a geologist is I had heard about Wally, I had heard about the Empire Formation, and when I get out there, there's actually more than one group of rocks. Formations of rocks are rocks that form at the same place at the same time, roughly in the same kind of conditions. And this does not look like the rocks in the last several photos. This is the Coos conglomerate. A conglomerate is a rock that mixes together a whole bunch of different things, and it takes a really lot of energy to move huge boulders that can get mixed up in it. And one of the exercises I like to do with my students is that I put a handful of gravel and some sand and mud in a jar, and I swirl it around, and you only move the gravel when you're actively moving the jar, but it takes a really long time for the mud to settle out. And this is showing how much energy does it take to move a rock. Well, there are whales are large animals, that were ripped up in how much energy went into this rock and redeposited in a new place. What sort of thing is enough energy to move a whale-sized giant chunk of rock? A lot of energy. There are also other fossils that are previously described from here that unfortunately might be this case of sort of mistaken identity. One of the very few fossils published in the 2000s out of University of California, Berkeley, were these fossil shark vertebrae. But again, they don't have all these shells around them. So this might have been a chunk ripped out of the lower geologic layer and put into this new higher layer. However, this specimen sat in a museum for 100 years and nobody looked at it, so they didn't see what it looked like in the field. We also found a new whale skull. It does not look like much of anything, and this really highlights how much work goes into finding when you see stuff in museums. So this sort of brown little bits on the edges of some of these rocks, those are cross sections through bones. So we have a new whale skull. that is actually in the Coos conglomerate and looks like it's associated with a lot of these big chunks and shells that are from this high energy event. So pending permits to go collect it, that's another thing that I will be looking for a whole lot of volunteers, because again, whales are unfortunately large. And then finally, at the very, very top of all of these other layers is this really cool sort of little gravelly deposit at the very top. This is similar to Jack's photos, except for on a much sunnier, less wavy day. And what's really cool about this little tiny top that we drive along for a lot of 101 is this is actually remnants of the ice ages. You are driving on an ice age beach. And that ice age beach at Fossil Point, right near the Dairy Queen, has produced a fossil walrus. We don't have walruses in Oregon anymore. It's been a while since we've had walruses. And what's very cool about this is very definitely a walrus jaw. This is from that gravel at the top of Fossil Point, and that gravel is 80,000 years old. So this is telling a story of changing climates and animals and communities here on the coast. This could be another really cool student project because there is no paper describing this and saying, hey, by the way, there's an Oregon walrus, which is cool. So as a geologist, one of my big questions is we have these really neat fossils. We have these stacks of these different layers of rocks, but how old are they? And what can this tell us about this changing coastline and possibly even hazards associated? Most of the dates that have been done are people looking at the rocks, comparing them to other places and saying, yeah, this looks kind of similar, so I'm going to guess it's approximately this old. That is not necessarily great science, especially when this particular map is currently some of the most up-to-date ages, and it's from 1964. Some of our science on figuring out how old rocks are has improved quite a bit since then. And featuring Michael, who I drug around all over in the mud, but we found the whale. It was great. This is really showing this sharp contact between our Empire Formation that vaguely we think is like 15 million years old, and the Coos conglomerate that people said, oh yeah, it's on top of that other one, so it's probably the same age, right? In geology, when we have really, really sharp lines between two different rock groups, it typically tells you you're missing time. If something continuously is forming new rocks, it tends to be a softer gradient. Whereas if there is a line you can put your finger on, something has happened. A big disaster, a major event, or you are missing time. So what does this mean if we potentially have missing time, if some of these rocks are not the ages that people have sort of blithely assumed they were for 100 years? Well, it relates back to hazards. Structural geology, yet another thing we have a bunch of cool possible student projects in, is looking at how rocks are deformed, how they are faulted, folded, moved around through time. And this is a geologic map looking at Coos Bay. It's pretty messy and complicated. All of those different colors are different types of rocks from different ages. And then the really important part, all of those black lines, those are actually faults. We live in an area that has a lot of small faults because the coast of Oregon is being both uplifted and kind of crunched together while also being rotated. Don't worry, it's not all that scary in terms of geologic hazard, but it does mean that we live in this very complicated area. And this can be shown in some of these new images that we're developing, bringing in some of our biology side, and that we have some really, really brand new drone footage looking at Fossil Point that can show us both where we have suspiciously straight lines, faults, as well as some of our biology students are zooming in on these images and you can see individual mussels and sea anemones and different sea animals to think about where things are living and how that might even relate to structures in the rocks. Do marine invertebrates like faults or not? It gives them a little place to live that's maybe a little more protected. And finally, I'm trying to tie in a lot of the local oral tradition or oral indigenous traditions. So historically, one of our big questions is we get little earthquakes here on the Oregon coast, not too bad, don't worry about it, you've slept through many of them. But we do have the rare possibility of Cascadia megathrust earthquakes. This is the big one that gets talked about in newspapers, usually in far too sensational of a way. We have a rather amazing record here on the Oregon South Coast of what exactly happens when a Cascadia megathrust earthquake happens. The last one was in January of 1700 because people were here and watched it. We have stories about Thunderbird fighting with whale, Thunderbird dropping whale, resulting in the ground shaking, whale scooting back into the ocean, smashing his tail and sending a huge wave up onto the land. And this was recorded as having happened after the first full moon of the shortest night of the year. And this was able, paired with some records from Japan, to give us the exact date and time that the last Cascadia megathrust earthquake happened. Additionally, we have a lot of places that have these what are called sea stacks, so rocks that are out in the ocean. And many of our local oral traditions, including some from the Coquille tribe, talk about some of these appearing after events with Thunderbird and whale fighting. So whole rocks being formed and thrown up onto the ground or submerged into the ocean from single earthquakes. So we can tie a lot of this story together, looking at Fossil Point as this possible record of, remember that really high energy part for the Coos conglomerate? That might be a tsunami deposit from a Cascadia megathrust earthquake. So that's how I'm trying to tie all of it together with a really, really lot of different student projects that are possible. Here's another one of our SWOCC students with a innocuous looking, but actually really cool and unusual fossil from Fossil Point. This is a predatory marine snail. So most of the fossils that are found at Fossil Point are not described to science. And this is something that y'all could be doing. So yay, come work on Fossil Point. It rocks. More people. Questions? Yeah.
One is, do you have an approximate date for the middle fossil?
Ooh, that's a loaded question. I think Wally and Kin are in the 15 to 18 million year ballpark.
What is the date of the McLaughlin building?
Oh, the very oldest one, 1901.
Because it shows the date.
Yep. Which is on a different iteration.
But thank you.
Yes. I mean, not that I should promote child labor, but
It counts as child labor, you pay it.
volunteer children labor. Absolutely.
Anybody else?
Yay. Oops.
Trying to go to our little placeholder for something better to look at, but. Okay. So I know that, I apologize, we're running a little bit later on schedule than what we had expected. We had planned to be done about 15 minutes ago, but we had some things that kind of, well, it was actually a good thing because we had lots of people out here looking at these amazing posters from Sociology. So we were trying to see it, give them a few more minutes to get people inside to get started. Next up, I just want to ask Dr. Coyner, who is our physics and engineering professor, to come up and talk a little bit about OSGC. OSGC is the Oregon NASA Space Grant Consortium, and both Dr. Coyner and myself are local reps for this amazing organization. A lot of these projects that you saw today were actually a lot of the students were participating in various programs that they have. One was the Orion program he'll share a bit about. And then the other one was STAR. And so with that.
So I figured we had enough slides already, so I ended up not doing slides for this because I do have an entire presentation on everything for the Oregon NASA Space Grant Consortium, but they have a number of programs that we've taken advantage of here at SWOCC, and it's helped us build out a lot of our science research. You saw a lot of the students in the early part of the presentations. They were all funded through our Oregon Internship Opportunity Network. Yes, we're all space nerds. That's how it became Orion. It just kind of stays there. The fact that a lot of us are tied into NASA, we try to make acronyms out of anything or make space references out of just about anything. I submitted a proposal this morning that was for our working with Oregon Sea Grant, which is another contingent of the various grant populations that we have from OSU. We ended up calling that one Shields because it just happened to work out that way. We'll talk about that one on a different day. But Oregon NASA Space Grant we've been a member as SWOCC since 2017. They let us in March. Every year they've had one, we have had at least one space grant scholarship winner, either as just a scholarship winner or as a STAR program participant like Cameron was, that where in order to get their stipend and their scholarship, they did an academic research topic where they did a white paper essentially on a given topic. In his case, it was the idea of nuclear propulsion for space travel. We have had students that have done that every year. They didn't have any this year, but in the past, they've also had a program called SCORE, which allows individual community college students to work with mentors at their local institution to complete sort of introductory, hands-on, high-impact experimental research. We've seen most of this in many of the fields. I know in physics and astronomy and engineering stuff, there's been a trend more to get students involved at younger ages in research, because for many years when I was in school, it was always, you didn't get into research until your junior or senior year as an undergrad if you had a small enough school, or if you were at one of the larger schools, they didn't pick on you until you were actually in grad school. But there's been a precipitous shift in that, in the sense that the earlier you can get started, the better it looks on your resume. And Oregon Space Grant actually allows us to do that. Up until the end of last year, we had a program that we ran through a faculty research award given to us by OSGC called Prisms. That funded a lot of the initial work that you saw with Mango. It funded a lot of the Starfall stuff. But it also allowed us, and she doesn't give herself enough credit, but it also allowed us to work a lot with Krystal to formulate sort of a pipeline to get us more students by having our student researchers go out and participate in outreach activities with younger scientifically minded students to mentor and inspire those younger students. All of that is made possible through various grants that we've had through Space Grant. I know we have numerous opportunities, and they have several opportunities every year. We apply for most of them. Sometimes we win them, sometimes we don't, but every time we get an opportunity to work on one of these projects, it allows us to bring in more students and more student research, and they all go in different directions. We started what would become SPEAR. It was essentially just doing atmospheric research with weather balloons. Atmospheric research with weather balloons did not appear in today's program. Not that we don't do it anymore, just that we have so many other projects so many other projects that are ongoing that have sort of taken on lives of their own. And it becomes a question of bandwidth, it becomes a question of people, and it becomes a question of time. But almost all of this is made possible through Oregon Space Grant and our connections with them. It's also facilitated a lot more projects that have tied off of like sister organizations from Space Grant, collaborations with different institutions that have started. A lot of our guest speakers that have come in on our physics and astronomy lecture series have come from connections that we've made through Space Grant. So there's just a lot of things that we build into our program that we've put together that is growing in all sorts of different directions, that all traces itself back to taking a chance and getting involved in a larger consortium and then trying to kind of not take full advantage of, but to use the resources and available programs and access that normally a little community college on the coast of Oregon, 2 hours from anywhere, wouldn't necessarily have access to. So we are extremely grateful to Catherine Lanier, Megan McGowan, and the rest of the Oregon Space Grant team that have helped us fund all these things. And just for those of you that are listening that may look at this and go, there may be an opportunity for me to do this. I got an email just yesterday, and those of you that are professors in the audience, you'll get an email from me about 30 seconds after I get home, where they're asking for new Orion internships for the summer. So if you have students if we have students that are interested in, college students that are interested in internships, we may have ways to design some for our summer term. We also may have some for high schoolers that are coming up through our other programs. So this is our start. This is kind of our culmination of our academic year, but this is where we're at, and we're still going on. All of the Orion presentations that you saw earlier, they actually have to give a final presentation to Space Grant in October. So between now and October, we'll still make a lot of progress with the data, and you'll see a lot of different stuff. And I will stop because otherwise I can rant for days.
If everybody want to catch their eyes, because it's going to get a little bright in here. Thank you, everybody. I wanted to allow more time for questions at the end, but since we're running so far behind, if you do have questions for any of our presenters, some of them might stick around a little bit. If for some reason you need to get going or they couldn't be here, we have our contact information on the table out there. We also have program information for all the different science programs. I also want to say thank you very much also to Dr. Coyner. We have Professor Morelli here, Professor Burgess here. We have Dr. Lynn McLaughlin, but there are also others that have helped with we've had many K-12 outreach programs that we have been able to have over this past school year. And without their help, it wouldn't have been made possible. Again, thank you to all the SPEAR students for all of your help with everything and your awesome job today with presenting. Our instructional dean, Doug Goodwin, is here. And then Dr. Allie McGinn wasn't able to be here. She is our vice president of instruction, but she had sent that she had wished that she was able to attend. She typically is attending these types of events and is a huge support for both her and Doug. Thank you so much for your continuous support. Also, thank you to our foundation board for allowing us to come and present to them, and our Board of Education for allowing us to highlight some of our SPEAR students recently. With that said, thank you all for being here.
Huge
thank you to you, Krystal.